Hi, my name is Eric Normand, and I'm going to talk about using test.check to test stateful systems that change over time. Um, Usually, the difficult things with those are that they're concurrent and sometimes asynchronous. So I've got a little bit of experience doing this. I was working on a system that was like a database that had to work across different browsers, and I used test check to make sure that it worked the same in different browsers. And so I'm going to talk about those experiences. You might know me from purelyfunctional.tv. It's my company where I teach Clojure. There's a nice newsletter if you want to sign up. Please go to purelyfunctional.tv and check it out. All right, so a little map of the talk. First, I'm going to motivate why we need to talk about test check in terms of stateful stuff. Then we're just going to jump right in. We're going to build a stateful system and then test it. Then we're going to add concurrency, then go in and make it more async. And then we'll talk about how we can take this further. So generative testing, also known as random testing or property-based testing, is something that has actually been in the Clojure community for a long time. I've been doing research to figure out, this background research, and I found talks going all the way back to like 2010 about generative testing. I actually did generative testing with QuickCheck and Haskell back then, and I was very excited when it started happening in the Clojure world, like really started picking up. The first time I realized it was happening was Reed Draper's talk at Clojure West, and John Hughes being the keynote speaker. That's when it really started to pick up. And of course, Benjamin Pierce gave a talk in 2015 about generative testing of Dropbox. And Clojure Spec, which came out last year, has test check integration built right in. So like, if you're not learning this, it's time to start learning. So I'd like to share my experiences. Test check is a very functional tool, meaning it's really good for testing pure functions out of the box. Now you can test stateful stuff, which we'll get to, but it really needs a little bit added on top of that. So let's jump right in. All right, first, let's build a little database. We're not going to actually code it, but we'll specify it. It's a key value database. It might be in memory. It might be on a different server. You have to communicate over the network. Whichever, regardless of how it is, these are the operations on it. And we're going to treat it like a black box, so we don't even know what it is. So you can create a database, you can clear it, that just gets rid of all the keys and values. You can store a key and value pair in the database, which will overwrite a previous key if it's, if that same key is there. It'll overwrite a previous store if the same key is there. Delete will remove whatever is stored for that key, and we can fetch the value for a key, and we can get the size of the whole database. How many key value pairs do we currently have? Now, I just want to say that there are no errors possible. So if you delete something that's not there, that's fine. It's not going to throw an error. It'll just, it's an idempotent operation. You can delete twice in a row, and that's fine. All right, so we want to test this database. Traditionally, if you're using like example-based tests, not generative tests, but example-based tests, you would do something like this. So you define a test called store contains, you create a database, you define some test data, a key and a value. You'll store that key and value in the database, and then you fetch it back out to make sure that it's the same value that you stored in. So there's an example. Here we want to test that store should overwrite old values. So if we do two stores, the second value is what we want to see. So let's store two values with the same key, store 1, store 2, and then we're going to fetch for that key, and it should be equal to v2. Okay, it's very, this is the kind of stuff I've done a lot in my career. Clear empty. So we want to say that it's empty after we clear it. So we're going to store a key and value, we're going to clear it, and then we're going to check to make sure that it's 0. Okay? So this is a very simple kind of test. It's very common to do this kind of test, but there's something unsatisfying about these tests. Like, it makes me want to write a test. Well, what if I store 7 key value pairs in there and then clear it? Will that help, right? But then, of course, it makes me want to think, well, what if I store like 100 in there? And then you start having loops, and you're generating random keys, or it's starting to get difficult. Like, you need some help. You want a library to help you. So why don't we do something like, instead of saying given this input, oh, and I should mention, it covers lines. So if you did a coverage report, you'd see, oh yeah, fetch got called, store got called, delete got called, all the things get called. Maybe even all the lines in delete got run, all the lines in fetch got run, because you didn't have many conditionals, let's say. But you're still not testing like interesting cases. Interesting cases are stuff like weird Unicode characters in your string, right? I mean, we've all been dissed by that. Okay. So we're saying right now, given this input, we expect this behavior. But what we want to say is given any input. So we want to test all these weird cases, the empty strings, the really long strings, the funny Unicode characters. We want to test all that too. But we also don't trust that we're going to be able to generate interesting cases ourselves. All right, so we're going to use test.check. Super quick introduction. You don't have to like totally get it. This is just an overview. When we get to the actual tests, we'll go deeper into it. So 3 big concepts you have to understand. Generators, they're things that generate random test data. Okay, different types. You can generate random test data. Properties. So this is a thing that will test an expression given that random data. So we had some test expressions like the value v equals fetch dbk, right? So we want to say that the value is the value in the database is the one we expect. All right, and then shrinkage. I don't even know if I need to go over shrinkage, so we're gonna. Okay. No, I should go over it. This is something we'll get to a lot later, but shrinkage is you generate this really big thing and it fails. But you don't know why it fails. It's like a 7,000 character string. Like, why did this one break? So what shrinkage does is it will try to reduce the size of it. So it's trying different characters, see if it still fails. It'll remove characters, see if it still fails. If it still fails, it keeps trying. Oh, I'll take out some more. Let me see if that one still fails. And it's doing this systematically, so it can get rid of a lot. And then it'll shrink it all the way down and be like, oh, this one Unicode character is breaking your database. That's very useful because you don't want to have to figure out by hand why that 7,000 character string is breaking. All right, so some generators. These are 2 generators. We're going to generate keys and values, and they're both strings. So we're just using gen, that's the generator namespace, and string. And some properties. So we're going to convert these old tests into test.check properties. You'll notice that they're basically the same. So we're defining store contains, it's a property for all returns a property. So check, that's the test.check namespace. So for all k and v, which are a key and a value, so we're going to be generating random keys and values. So for all k and v, we'll just do this expression. So we're going to create a database, just like before. We're going to store k and v, and then we're going to fetch the k, the value for k, and compare it to v. That's it. That's our property. You'll notice it's just like the let that we had before in the old test case, except now we're not assigning it a fixed string like A or B. We're generating these random things. And the for all sets up a property that you can then run and test it as many times as you want, always with new data. Okay, let's look at this second property. So store overwrite. If we store a second thing, we expect to see the second value. So we're going to generate a key and two values, and then in the test we're creating the database, storing once, storing twice, and then checking that we're getting the second value out. All right, clear empty. So if I store something in it and then I clear, it should be empty. So we're going to just store a random key and value and clear it. Okay. So this covers a little bit more than what we had before. I mean, a lot more. Some interesting stuff is covered there. We talked about these weird Unicode characters that you would never type yourself, like you probably don't even know how to type them, empty strings, and very long strings. But the problem is the operations are fixed. So I'm only doing one store before I clear, right? So if we take a look at our properties, what we're saying is given any input for this sequence of operations, we expect this behavior. But what we really want to say is for any sequence of operations with their input, we expect it to work like some other thing. Right? So what is that other thing? Well, this thing that we're thinking of is called the model. So we have the actual system under test, which is the database, and we want to model its behavior in some way. We want a thing that acts like it and that we trust, that we can compare the two together. So if only we had an in-memory so it's fast, immutable, so that it's functional programming, key value store. Well, we do, it's called a hash map. And so a key value database is basically like a hash map with some other qualities, like it's durable, or it's mutable, or things like that. So if we just say, well, we're going to ignore the durability, we're going to ignore the mutability, we've got hash maps, and we can compare them. And we expect them to behave for this particular set of tests. We expect this model to model the behavior of the database. Okay, so here's steps of how we're gonna go about this. Step one, we're gonna build our model so that it's built in the same way as the thing we're testing. So we're only going to model the stateful behavior. That's like the fetching and the size and stuff. Those aren't stateful, meaning they don't mutate They don't mutate our database. Okay, so we're only checking, what do I mean by this? We're only checking that we're making the proper changes that we expect. Okay, so right, so HM_create, that's our constructor. It's going to create an empty hash map. Clear, we just throw away the hash map and return a new empty one. Store, it's a soch. Delete on a hash map, well, that's dissoc. Fetch, well, like I said, we're not concerned right now with the actual value we get back. We just want to make sure to say that it doesn't change the database. And size is the same. We don't really care about the size of this hash map for this. We just want to make sure that it doesn't change it. Okay, so now we're going to take these operations and turn them into generators. So we have operations for a database and we have the same operations for a hash map. What we want to do is run these operations on both and then compare to make sure that they have the same answer. And so what we're going to do is make generators out of those for each operation, right? Okay. So it's easy. Clear, we're going to generate, so gen return always returns, it's just a constant generator, always returns the same random thing, same thing. It's not really random. So it's just going to return the tuple that starts with the keyword clear. Same with size, it's just going to return a tuple with size. Now store is going to return a tuple, and the first thing in the tuple is the keyword store. Second thing in the tuple is a key. Third thing is a value. And of course, they're random. Delete is a tuple with delete and a key. We don't need a value for the operation of delete. Fetch needs a key. And then we're going to make a vector of these. Now, one of will randomly choose one of these generators and then generate a value from it. So we're going to get a vector of a random vector of all of these operations. Cool. We're getting a random, so a vector, so a sequence of operations. The length of the vector is random, and the particular operations and their order, that's all random. Okay, now we're going to make two runners because we want to run the database one and we want to run the hash map one using the same data, the same operations. So we're making a runner. So this is the database runner. It's just going to iterate through the operations and then it's going to match and dispatch. So it's kind of boring code. Clear, we'll just call clear. Size, call size. Same thing with the hash map, but this time we're going to reduce because it's just an immutable value. And the match looks kind of the same. Clear calls clear. And you can see here how returning the database from fetch is what we want to do. We just want to say that it hasn't mutated the hash map or the database. Okay, so at the end of this process of running both of them, we would need to check, are they equivalent? Are they the same thing? So we're defining a little function here called equiv. First, we'll see if the sizes are the same number of keys. If they're not, it's not equivalent. And then once we know that the sizes are the same, we can just check that every key in the hash map has the same value as in the database. So we're going to fetch out of the database the key, compare it to value. All right, so now we can compare a hash map and a database. So here's our property. for all sequences of ops, we're going to run the hash map version of it on a fresh hash map. That'll be our HM. This is the answer we expect. Okay, and then we're going to create a database. We're going to do the DB run. So we're going to run the same ops on that database, and then we check if they're equivalent. All right. So if you run this, it'll probably work. Meaning you'll pass all your tests. Then if you start to look closely at what gets generated, you'll realize that there's just a little bit too much randomness in here. What we're doing is generating random keys 3 different places: here, here, and here. And if we do a store with a random key, and then we generate a different random key, which is very likely when the keys start getting very long, we're going to try to delete that other random key. It's not really testing what we want. Like it's actually very unlikely that we're going to test that we're deleting something that we just stored. And we kind of want to test that. We want to test that we can delete something that we didn't store, and we want to test that we are deleting something that we did store. So we need to decrease the randomness a bit here. So what we can do is, it's a little trick. This is one of the things that I learned through experience. Okay, so gen clear and gen size, they don't change because they don't have keys. But gen store had keys. So we're instead of making a generator directly, we're going to make a function called genStore that takes the keys to choose from. And then we're just returning the tuple, but instead of generating a random key, it's going to select a random key from that collection. And then it's going to generate a value. So delete is the same. We're making it into a function, and we're going to choose a random key from there. Fetch is the same. All right, now here's the trick, is we're making a new function that's going to return a vector of these, and then we're going to pass the same keys to each of them. So now they're each choosing from a small collection. Small, it could be arbitrarily large, but the same collection of keys. So they're much more likely to collide. And then gen ops, we're just going to, so this gen let, is similar to a regular Clojure let. Keys is going to be bound to a random value from this generator. So we're saying a non-empty vector of keys. Okay, so we're generating a vector of keys and then passing it to genops star. So then that will generate our vector of operations that is subselecting on these keys. Okay, now when we run it, we start to actually see stuff like storing and then deleting, storing the same key multiple times, that kind of thing. It covers a lot of interesting stuff, like long sequences of operations with interesting behavior like that collisions that we talked about. And it's also got stuff like clearing 10 times in a row. Like you would never do that in a test, or you might do clearing 10 times in a row, but there's always some other weird thing that you would never do. So we've gained a lot here. The thing about it is it's not concurrent. We're running the sequence of operations in sequence. We're not having threads doing stuff concurrently, and so we do want that. So let's take a look, English sentence of what we're doing. For any sequence of operations, we expect it to work like this other thing, like a hash map. Well, what we want to say is for n threads running their own sequences of operations, we expect it to work like a hash map. Okay. So you want to test the concurrency of this and that it still works as you expect. All right, so let's make a new runner that makes a thread. So run in thread. We're going to create a thread, and we're just going to do db run in that thread, and we're going to start the thread. It's very simple code here. All right, so now we want to take multiple ops sequences. That's what those are. So different threads are going to be running different sequences of ops. So we're going to give a collection of those. And we're going to just call run in thread on all of those. Right? So each item in this vector is getting run in a different thread. But they're all going to finish at different times because we don't know when they finish. The threads are not that communicative, so we have to add to it. The easy thing to do is create a promise in each thread, and we're going to deliver on that promise after we finished doing our db run. And so we can return that promise from this function, and it'll be a signal for when the thing is done. So what we need to do now is, instead of run bang over them, we map over them and keep the promises that are returned. Now we're going to do run all of them to make sure that the laziness is not a problem. And then we're going to deref on all the threads, and that'll block on each one until they're all done. Okay, so here's another problem that you'll run into, which I ran into, is that you need to make sure that all the threads start at the same time. You notice we called start immediately on it, and usually with very short sequences of operations, it can actually finish before the last one is done. So you might create, let's say you created 1,000 threads. Well, this one, you start here and you just work your way down, you're doing do run. This one could finish before this one has even gotten to it. So we need to fix that. So there's a little technique in parallel programming. It's called a latch. So we're going to pass in a latch. It's like a latch on a door. Don't let the, or a latch on in a race. Like, you want to make sure all the horses in the race start at the same time. So you have a bar that goes across all of the doors of the in front of the horses, and then you have one latch, and you pull the latch, and the whole thing falls down at the same time. That's the idea. So we're going to pass in that latch. It's actually a promise. So we still have that done promise. Now what we're doing is we're going to deref our promise, our latch, and it'll block. So we're starting the thread, but then it just immediately blocks. And we run, we deliver when we're done. That's all the same. Now, the first thing we do is create the latch, and we're going to pass that in to all of our run and thread calls. We start all the threads by do running them. Then we're going to deliver on the latch. Doesn't matter what value we deliver. And then we block on all the threads, all those done promises. Okay, well, this now should be pretty easy. What we're doing is we're going to generate ops A and ops B, two sequences of operations, thread A and thread B. We're going to call thread run on those with a fresh database and check if it's equivalent to the hash map. The question is, what does equivalent to the hash map mean here? Well, in this case, which is actually wrong, we're just going to concatenate the two sequences of operations and run them with our hash map runner. But we'll get to fixing that in a second. I do want to come back to this because now what we've got is we're randomly generating this operation, we're randomly generating this sequence of operations, and it's very unlikely that the keys will collide in interesting ways, but across threads. So we need to have that same trick. We need to do it for this sequence of threads. So what we're going to do is define a new generator. It's actually a function that returns a generator and takes a number of threads that we want to generate. And it's going to do the same thing. It's going to generate a bunch of keys. And then this time make a tuple full of n gen ops sequences. So we're generating n random sequences of operations, and they're sharing keys between them. All right, so now we have collisions, and so we're just going to do like a destructuring to get those two out. It's the only difference here. All right, so here's the trouble, is we just concatenated A and B and ran it through a hash map. But we don't know how those operations actually interleaved when they were run on the different threads. If you are not familiar with interleaving, the thing is threads are running on different cores. So you have thread A is running on core A, thread B is running on core B. They just run their programs, and they're sending messages to the database, but you can't control what order the messages actually get to that database. And you run it 2 times and they'll be in a different order. And this is the big problem with concurrency in general. So we want to be able to take that into account in our model. So our model right now, where we're just concatenating the two, is not taking that into account. We know that the order of operations matters. If you delete first and then store, it's different from storing and then deleting. So what we need to say is that some possible interleaving happened. The most we can say is that the database is equivalent to some possible interleaving. So what I have here is some short code that generates, given a sequence of values, it will generate all possible interleavings. Yeah. So this is actually pretty fast. It's cubic or something. It's very, very bad algorithmic complexity, but it's generated lazily, and we turn it all into a set at the end, so I guess it's not so lazy. But the idea is you can generate all possible interleavings, and then you can iterate over every single one, looking for one that matches. Okay, so now how do we do this? So ops I is going to have all possible interleavings in it from ops A and ops B. And so we're going to look for some interleaving that is equivalent to the database. And if we find one, that's fine. We're done. And we pass. If we don't find one, we go through all the possible interleavings, we still haven't found one that is equivalent to DB, then we fail. Okay, so like I said before, we don't know, we can't control how the things interleave, and every time they run, they could interleave in a different way. So that's a problem, and the reason it's a problem is you run the test once, it passes, you run it again, and it fails. and then you run again and it passes, and you don't know why. I mean, you know why. It's some race condition, but you can't debug it. John Hughes and Benjamin Pierce have come up with two possible solutions. One is to check that you run it 10 times. I mean, you repeat it. You run the test 10 times. The two threads, you run them 10 times. And if there's two possible interpretations, you could say the test fails if any of those runs failed. Or you could say the test fails if all of the runs fail. And they've actually got two papers that contradict each other on that, which one is better. So try both. They're not hard to write. They basically just trade some in every. All right, so another thing that could enhance your test is to run a setup before you start the different threads. So this is a random sequence of operations that runs on a single thread in sequence to kind of get the database into a certain state before you do the other stuff. And so basically that means we're just going to generate a third sequence of operations and run those first. So we're going to do db run ops s, which is the setup, and then we're going to thread run the a and b. And we still run everything 10 times. That's just a little enhancement. Okay. Timing. Okay, when you have stuff that's concurrent, you start to have timing issues where, because messages are passing around, if you wait a little bit longer, then you find the bug, right? But if you send the message too fast, it won't have a bug. So we need to include that in here. What John Hughes found was that the sequences of operations that he was generating were really long, and they wouldn't shrink. And he determined that the reason is like they were doing like 100 fetches in a row, and he's like, why would it need to do 100 fetches in a row? Well, it's because each fetch took a little bit of time, and you add all those 100 up, and it was the right amount of time to wait. And so he made it so that things would shrink to a sleep. So we need to add a sleep operation. So here's sleep, just random amount of time, number of milliseconds, and it'll be our new operation. But here, while we're here, I'm actually going to reorder our operations. This is the same operations, except we've added sleep, but I've ordered them from least mutatey to most mutatey, like most destructive, you might say. So sleep doesn't even touch the database. Size just asks for, one global value. Fetch, well, it's probably going to have to do a little bit more. Store is going to overwrite, but delete actually removes information that store leaves in, and then gen clear, the clear deletes everything. So I've kind of ordered them that way because in the one of, things shrink to the earlier side of the front end of the list. So a clear will shrink to a delete will shrink to a store, etc. And so they all will shrink to a sleep, and then they could be removed as a sleep if it's unnecessary. And this kind of thinking about shrinking, is only important if you're noticing that you're getting longer things that won't shrink. And start to think about how to make it shrink better. All right, so we're changing our runner. We're just adding sleep. And of course, we don't need to do anything in the hash map runner. We don't really need to sleep for that because we know it doesn't depend on timing. Okay, well, now we've got this really interesting thing that's running really well. It is testing multiple threads against a model with the ability to somewhat control the interleaving, in a random way, to control interleaving with sleeps, so that you can, in a very simple way, control how things get interleaved, so that you can make your tests more reliably fail. One thing that we have not done, and we purposefully left it out, is check that each fetch that we do actually gets the right answer. We only check at the end whether it's equivalent to our model. We don't check that things are the right answer the whole time. And so sometimes that's really important. Like just to know that the thing did get stored in the middle there, or like what the timing is for storage, that kind of thing. So John Hughes and Benjamin Pierce have developed these systems for developing a state machine model that models the entire trace of everything that happened. So the idea is you build a trace. So every time you do a fetch, you remember that. So each thread will have its own trace of everything that happened. And you can then run, so you're doing all these operations, you trace it, and then you're actually validating your trace instead of validating this model at the end. It's still a model, it's just a more formal model. So let's see, the trace, you record what happens when meaning what order. You infer things that you couldn't see, and the inference is very simple. For instance, in Dropbox, the Dropbox testing, they just infer a downsync and an upsync. Like, well, I read the value, thread A read the value from thread B. There must have been an upsync from B and then a downsync from A. And it's a way of modeling like what traces are possible, and it's actually a little bit more efficient than generating every possible interleaving. So that's a savings there. Another thing that John Hughes did, which was really fascinating, amazing to read about, is these temporal relations. So when timing is very important, you want to be able to be a little bit fuzzy about something. So you want to be able to say, well, the message that this person has logged out has not reached the server yet. So there's a time period where maybe if you ask the server, he'll say that the thing is logged out, but maybe it won't, but he may have been logged out already. And so you can start to reason about the behavior. Maybe this message will reach his client, or maybe it won't, because maybe he's logged out. And although you say, well, after 100 milliseconds, he should already be logged out. There's no doubt. So that gives you some play to better define your tests and your models so that you can see how things work. Okay, I would love to have a couple of references here. There's a page I've made for this talk on my site. I haven't made it yet, but I will. And it has references to papers and talks about using test.check. You should learn test.check. I would like to make a course on it on purely functional TV, especially since it's very important for using spec. So, yes, thank you very much.